Hello, my name is Zachary Strout, and this is Physics 2 Lab 4 Circuits. For a little overview, first we're going to go over the introduction, as well as the purpose, the fundamental principles and equations, and the main results, and then the experiment, and the setup, the experimental data, the calculations, and then a discussion. So for the introduction, the purpose of this experiment was to examine circuits containing resistors in series and parallel, as well as to examine ohmic resistors and capacitors and measure the potential difference and conventional current in the circuits. So some of the fundamental equations and principles, we have Ohm's law, which states that V is equal to current times resistance, the loop rule, the node rule, that the current in is equal to the current out, and capacitance. And the most significant result of this experiment is that the time constant, RC, was found to be 5.91 seconds. So the first part of the experiment, it was predicted that I1 was equal to I2, which was equal to 0.02 amps. We know that I is equal to V divided by R. Here, the V was equal to 3. The total resistance is 147 ohms. And then using that equation, we find that the current is 0.02 amps. And it was found that the actual current was also 0.02 amps. And doing the reverse connection, the readout on the ammeter remains the same. So in the second part of the experiment, after replacing an ammeter with a voltmeter, overall we find that the C to D was equal to negative 0.96, and E to F is equal to negative 2.04 V, and A to B overall is equal to 3V. And using the loop rule, we find that the total V is equal to 0. And in the second part of the experiment, we can see that from A to B, the voltage increases, and then from B to C, it's pretty steady, and then it starts decreasing from C to D, steady at D to E, and then from E to F, there's also a steady decrease, and then from then on, it remains 0. So for our calculations, we find that the resistance at 47 was 48 ohms, and R100 was equal to 102 ohms. The resistance of the wire was 0 ohms, and the resistance of the ammeter was 0 ohms as well. And then for the ammeter connected in parallel with the 100 ohm resistor, both ammeters read 0.06, and the addition of the voltmeter does not change the ammeter reading because of high resistance and voltmeter. And then for the RC circuit experiment, we found that for the charging battery attached, at 10 ohms it was 18.13 seconds, at 20 ohms is 20.25 seconds. When discharging the fully charged battery at 10 ohms, took 38.79 seconds, and at 20 ohms it took 40.11 seconds. So here are our major data and calculations using the trend line for the natural log versus time. Find that y is equal to negative 0.1691 x plus 0.0069, and then using the calculations on the right, we know that RC is equal to 5.91 seconds, as negative 1 divided by RC was equal to negative 0.1691. And for our discussion, what if you were doing this lab in real life and used an actual ammeter instead of an ideal simulated ammeter? What's different about a real ammeter, and how would it have affected the circuits you hooked it up to? So the measurement for current would be lower because in real life, an ammeter has a slight amount of resistance, and in this experiment, the simulated ammeter has 0 resistance. So what if you were doing this lab in real life and used a real battery to charge a real capacitor with no resistor in the circuit? How quickly would our ideal model predict the capacitor to reach full charge. Would this prediction happen in real life? So in real life, the real capacitor would take much longer to charge than our ideal model, and due to resistance, no capacitors can realistically charge instantly, so this would not happen in real life. And that is all. Thank you very much.